One more type of integral to add to our pile of things we can do. Let's consider the function 1 over x squared. Now, what happens in this function as x gets larger and larger? What's the graph of 1 over x squared look like? As x gets bigger and bigger and bigger, this thing is getting closer and closer to 0. So let's say I wanted to do an integral. So I wanted to go the integral from 1 to some number. We can compute this integral. The only place 1 over x squared has a problem is 0. So as long as I'm integrating from 1 towards the right, so t is some positive number bigger than 1, this is well defined. Do this antiderivative for me. What'd you get? Because this is x to the negative 2, its antiderivative is x to the negative 1 over negative 1. But that x goes in the bottom, right? So it should be 1 over x. Oh, it's negative. Plug in t, plug in 1. Minus negative 1 over, that's plus 1, isn't it? The second part. That's a plus 1. So I can write that as 1 minus 1 over t. Please notice that as t gets larger and larger and larger, this is still well defined. That limit is perfectly well defined. But if that limit is well defined, then I could say that the limit here is well defined, because this left side came about as doing this integral. So I'm going to make a new definition. An integral that goes off to infinity. Oh, f of x dx. I'm going to define this to be the limit as t goes to infinity of the integral from a to t, f of x dx, as long as that limit exists. And is finite. So now I can actually integrate when my upper limit is infinity if I do it with this limit idea. This is called an improper integral. By the way, if it works going off to positive infinity, should work, going off to negative infinity. Again, provided this integral, the limit exists and is finite, then I can define such an integral. Now, since this is a limit, but we're going off to infinity, we tend to think of this as an approach. The way we thought of a limit, for every epsilon, there is a delta sort of, I don't want to do that precise anal retentive definition, but it's hiding in there somewhere because I'm using a limit. But since I'm not actually approaching a number, I'm approaching infinity, we think of this as getting closer and closer and closer. We're going to say that these integrals converge to this limit. But that means if the integral doesn't exist, or if it's not finite, then the integral diverges. So now I can write the integral from 1 to infinity of 1 over x squared dx. And since we've already computed this integral, we know the value for this. This is 1. Questions? Try this one. Not all that much different. If the limit exists, if the integral converges, find its value. If it doesn't exist, let's explain why. The first thing I have to do to solve this sort of problem is rewrite this as a limit, because that's what our definition is up here. So I first say this is really the limit as t is going to infinity of the integral from 1 to t, 1 over x squared plus 1 dx. Now infinity itself is not part of the integral, so I can try and do the integral with all the tricks we already learned. Do we know an antiderivative for this? Yeah.
Would you be able to, so would you have to do something at the bottom, and it would be 1 over the natural log of the absolute value x squared plus 1.
If that's the case, then what you're doing is you're making a u substitution for the bottom, right? Think of it as 1 over stuff.
Yeah.
What's du?
That's be a 2x.
I don't have a 2x. I have a 1, but I don't have a 2x. The 2 I'm not worried about. What do I do with the x? I can't fudge the x. So as much as I want to do that, Leo, I don't have the x I need. I could try and do integration by parts. Maybe build an x in there somehow. I think that might be more trouble than it's worth. Aha. This one's on my formula sheet. Only it's written 1 plus x squared, isn't it? That's my inverse tangent. So I've done the antiderivative. I can plug in and I get the inverse tangent of t minus the inverse tangent of 1. And now I get to ask you all a trig question. What's the inverse tangent look like? Yes, this is where we have to do another math dance with our arms. Tangent itself, the graph of tangent, has asymptotes, right? There are vertical asymptotes in the graph of tangent, which means its inverse has horizontal asymptotes, because everything that was going up now goes sideways. What is that first vertical asymptote on the right in tangent? Where's the first place for positive values that tangent is undefined? Pi over 2. And if that's my vertical asymptote, that becomes my horizontal asymptote. So I can say to myself, oh, if this is the graph of tangent, then the inverse switches the x's and the y's I get a graph that looks like this. But the important part about this is that horizontal asymptote. Why? Yes. But how does the horizontal asymptote here help me over here? Bingo. If I want to do the limit as t goes to infinity of the tangent inverse, I need to follow this graph off to the right. And that means that I know this right here is pi over 2. What is tangent inverse of 1? What's an angle whose tangent is 1?
Pi over 4.
It most certainly would. And pi over 2 minus pi over 4 is a number. Pi over 4. Which means this limit exists and is finite. This integral converges, and we found its value. So the whole idea here is that I'm going to need to figure out what happens as I go off to infinity. Now, for those of you who took discrete math, what I'm really asking about is a big O idea. For those of you who will be taking discrete math in the spring, we will see this again. But we did this last semester. We did L'Hopital's rule. We did limits as things went off to infinity. So we know, I say that with a grain of salt, we understand how to do limits as things go off to infinity. Questions? Our definition said the limit from a to infinity. So there's no requirement that I start at 1, which means I could just as easily do the integral from 4 to infinity, 1 over x squared dx. That would make sense as well, and it should converge. Only the number will be different. because instead of starting at 1, I started at 4, I'm going to get a different actual physical value for this one. But it should still converge. Why do I know it should still converge without doing anything else?
You know by the x squared, the p is greater than 1.
I don't know what p you're talking about yet.
Like the series, we're talking about a series.
I haven't touched series. Again, I don't know what you're talking about yet. Hold that thought. I can go back to the very first problem we did, which was 1 to infinity, 1 over x squared, right? So if I think about the integral from 1 to infinity of 1 over x squared dx was equal to 1, that's the area in the right-hand part of that picture, yes? Well, now I'm going from 4 to infinity. Isn't that a smaller area? Didn't I just take off a chunk? I knew the value was 1, now I'm taking away a piece of it. The answer to this problem should be a little bit smaller than 1. So I don't even have to do this one to know it's going to converge. I should be able to do it using the same exact technique we did on the first problem. But I can say, oh no, this is going to converge even if I don't know what it is first. The integral from 4 to infinity, 1 over x squared dx, becomes the limit as t goes to infinity. Integral 4 to t, 1 over x squared dx, which we did as negative 1 over x, 4 to t, negative 1 over t minus negative 1 over 4. What happens is t goes off to infinity to 1 over t. Fumble. It would, which means I get 0 minus negative a quarter, which is 1/4. So Dom, if that 1 over t is going to 0, I think that's somehow a critically important part of what we're doing. That idea that that upper limit is going to disappear, or is going to be a known finite value, right? So what happens if we try this one? I'm fortunate, again, this is an integral I know how to do. First thing I do is I make it a limit, but then I have to do the antiderivative. So antiderivative of 1 over x. Which means I get the limit as t goes to infinity of ln of t minus ln of 1. But ln of 1 is 0. So really, I need to know what happens to ln of t as t goes off to infinity. Yeah.
It'd be like infinity because
That graph keeps going up. Now, technically, we could say that this limit has a value of infinity. But a value of infinity doesn't make sense in the real number universe. So while I would like to say, oh, this limit is infinity, that's not a valid option. And notice we said when we defined this, our limit has to exist and be finite. And that means this integral diverges. We might even say it diverges to infinity, but that's not really necessary. I can just say, hey, it diverges. So 1 over x squared worked. 1 over x doesn't. An integral is a measure of area. The way we're using it, an integral measures areas. So let's take a look at the graph of 1 over x and the graph of 1 over x squared side by side. And if we look at the graph of 1 over x squared, page 529, and the graph of 1 over x, they look pretty damn similar, don't they? But this has an area of 1, even as we go off forever. This has an area of infinity. So in spite of those two being really, really physically similar, this is much, much, much larger than this one. We know that when we do 1 over x squared, it converges, we get a value. What if we do 1 over x cubed?
as well.
Then let's try it and find out. Let's do this one from the top. Limit as t goes to infinity, integral 1 to t. 1 over x cubed is x to the negative 3. So when I do the antiderivative, I get power rule. X to the negative 2 over negative 2 from 1 to t. Now negative powers go on the bottom, so that's going to be negative 1 over 2x squared from 1 to t. And when I put in t, limit, can't forget my limit, negative 1 over 2t squared minus negative 1 over 2 times 1 squared. What happens to that first term? It's 0 again. Minus a minus 1/2 is positive 1/2. This converged, we found its limit. I have a sneaking suspicion. Try this one. What's my antiderivative this time?
It'd be 2 times the square root of x.
Well, that means I get the limit as t goes to infinity of 2 root t minus 2 root 1. What happens here?
It would be infinity. It's infinity minus 2.
The square root of something huge is huge. Leo, I think you were on the right track with the idea of generalizing this. So let's take a look at what happens to 1 over x raised to any power. Which I would write as x to the negative power. And then by the power rule, I get x to the negative p plus 1 over negative p plus 1 from 1 to t. I want to put that power in the bottom. It means I put a minus in front of it. And it'll be p minus 1 on the bottom. I'm going to take that 1 over 1 minus p part and pull it out front, because that's just a number, this part. Now, the real question is what happens to that fraction, 1 over t to the 1 minus p? Well, that depends on the value of p. Look at what we had earlier. When p was 2, right, 1 over x squared, then this became, no, I've written it backwards, p minus 1. I wrote it one way and then wrote it the other way. This should be 1 minus p. This should be p minus 1. Eesh. Apologize, people. Put it in the bottom. I have to make the power negative. So negative p plus 1 becomes p minus 1. If p is 2, then I get 1 over t to the first. If p is 3, I get 1 over t squared. When p was 1/2, I get 1 over p to the negative 1/2, which goes back up top. When p is 1, I get 1 over t to the, I get the ln, right? Aha. If the bottom power is positive, then this is going to go to 0 as x goes to infinity. If that number is 0, then we had 1 over t to the p, and that meant we got the ln, right? I'm sorry, t to the first. And that went off to infinity. If p minus 1 is less than 0, then 1 over t to the p minus 1, this is a negative number, which means it really should go in the top. Because 1 over p to a negative, 1 over t to a negative, should be t to a positive. And a power that's positive is going to keep growing. No matter what, even if it's a square root, it's just going to grow slowly. That's going to get big. And this means this diverges. That means I can make a general statement about any integral of the form 1 over x to a power when I'm integrating from 1 to infinity. This converges only when t is bigger than 1. I don't care how much bigger than 1. 3 is bigger than 1. 17 is bigger than 1. 1.135 is bigger than 1. Doesn't matter. So 1 over x is my dividing line. It separates integrals that converge from integrals that diverge because of the logarithm. That's a switch between nice integrals that converge and integrals that diverge. I'm going to use this a lot. So let's put a big star next to this. I'm going to need this. Questions? Yes. Yeah, it's only integrals who go from a to infinity. Technically, I should make that an a as long as a is bigger than 0. Why can't I use a less than 0? Right, because the function would have a big asymptote in the middle, and you can't integrate across an asymptote. It doesn't work that way. But one of the functions I did earlier didn't have an asymptote. That function is defined everywhere, right? No asymptote there. Which means I could really think of that graph as continuous from minus infinity to infinity. I could integrate positive infinity starting at some point. I could also integrate to negative infinity. That works. All I have to do is break it up somewhere in the middle. As a matter of fact, this is true in general. If you want to integrate from minus infinity to infinity, you just integrate from minus infinity to some point A, and then from that same point A off to infinity. But now both things over there on the right, both of those integrals have to exist and both have to be finite. If either one of them is an infinity, out the door. This actually comes in really, really, really useful in statistics. One of the functions we use a lot in statistics is an exponential. It's going to look familiar here. Turns out it's very difficult to integrate this function. We said earlier we don't know what the antiderivative is, but there is actually a way to integrate this function using definite integrals. Now, I will show you how to do that in chapter 10. But it turns out that this is a number. So if you graph this function, you get a function that looks like this. I don't know if you've ever seen a function that looks like that before. Any of you taken a proper stats class before? That's a bell curve. That's a normal distribution. That's the backbone of modern statistics. And the reason I divided by the square root of 2 pi is to make the area under this curve 1. That way, 100% of the things that could happen are represented by areas under that curve. More on that in chapter 8, and a little more in chapter 10. But that's the reason we try and do integrals from negative infinity to infinity. Questions? Maddie, you said that only works, that P thing only works from 1 to infinity. Well, it works from A to infinity, right? One of my limits had to be infinity. Neither of the limits of this integral are infinity. But we still have a problem with this integral. What's the problem with this integral? Well, it doesn't exist at 1? What's the square root of that if you put in 1?
0.
Square root of 0 is okay. My problem isn't that it doesn't exist at 1. The problem is that it doesn't exist to the left of 1. Which means it's not continuous at 1. It's only continuous from one side. All of my crap about integrals requires my function to be continuous. So I've lost half the side of my function. This is still an improper idea. I don't like having discontinuous functions. So what if I said we're going to cheat? And we're going to look at the function that goes just a little bit bigger than 1. And then we'll take the limit as we close in on 1. So what we've got is an example of a function that's continuous everywhere to the right of 1, but not at 1 itself. So what we're going to do is we're going to define our limit as approaching A from the right. If that limit exists and is finite, then our integral converges. Otherwise, it diverges, just like before. Which means I can try and do this integral square root of x minus 1. Oh, I apologize. Go back up here. 1 over. It's not root x minus 1, it's 1 over root x minus 1. That's really effed up, right? Leo, as you said, that as we get to 1, that goes to 0, right? And 1 over 0 messes with it. Yeah, so that's my reason for trying to do this. I want to fix that undefined part. I've still got an asymptote. Now it's a vertical asymptote as opposed to a horizontal. So the first question is, can you do the integral now that it doesn't have a 1 in it? What do I do? With u equals? If u is x minus 1, then du is just dx, and this becomes 1 over the square root of u. Du. That's u to the minus 1/2. So when I integrate that, I get 2u to the 1/2. Put it back in x. And I have 2 square root of x minus 1. So, limit as t approaches 1 from the right, 2 square root 5 minus 1 minus 2 square root t minus 1. The first part doesn't have t in it, so that limit only applies to the second square root. What happens when I plug in t equals 1 to that second square root? It equals 0. So this is 2 times the square root of 4. Square root of 4 is 2, that's 4, minus 0. It worked. I don't have to have an infinity in my limits. If I've got an asymptote floating around, I can try and figure out what's going on with that asymptote. Now, in this problem, the asymptote was on the left. And that's why we had our open parenthesis here on the left. But if your asymptote is on the right, this still works, the mirror image. You just take the limit as you approach from the left. Oh, and by the way, you can do it on both sides. If you're trapped between two, you split it up and go from the middle to the right or the middle to the left and do 2 limits. But they both have to work, just like they both have to work if we're going off to infinity. The asymptote can't be in the middle. The most important result I can give you is called the comparison test. F and G are continuous functions. G is smaller than F, but both of them are positive. For X bigger than A, if the top one is finite, then the bottom one must be finite also. If the top one converges, it traps the bottom one and it converges also. If the bottom one blows up to infinity, then it takes the top one with it. Which means if I don't know how to do the integral directly, I can compare it to something that I do know how to use. My best comparison integrals are those x to the p integrals. Because I just look at them and I know whether or not that diverges or converges. Just looking at the power. Oh, it's bigger than 1 on the bottom. Proof that's going to converge. Notice these are intervals from a to infinity, so I'm using that trick. And that means even though I have no idea how the integral 1 to infinity 1 plus e to the negative x over x would be done, I know it's going to diverge. This diverges since 1 over x is smaller than 1 plus something over x. This integral goes to infinity. It's got to take this one with it. Comparing is a powerful tool for us. This is the last section of chapter 7. Therefore, this is the end of the material for the first exam. Wednesday is question and answer day, and that includes the review sheet that's been up since day 1 of class. Our exam is Friday. See you all on Wednesday.